tumbling kernel now should be. And ideally, it should be informed by biological insights into what's actually happening with the cells.
For them, it's for the video.
Ah, hello. Hi, Giacomo. Yes, so we assume that basically this tumbling frequency is some function of the material derivative. So what I mean by that is like the change in concentration that the cell sees along its trajectory. So if I'm a cell and I'm traveling at velocity v prime, I observe along my path how the chemical is increasing or decreasing, and then I decide if I tumble or not. So this psi is simply a decreasing function. So if the chemoattractant is increasing, then I tumble less often. That's the idea. And so now you can actually go ahead and from experiments try to figure out a reasonable shape of this psi. But for now, it's just something that is decreasing. Okay, and now we need some assumptions that will give us this macroscopic description in the end. So here the assumption is that this tumbling frequency is a small perturbation of some basic tumbling rate. So if there's no other cell, like there's one single cell in the universe and you just put it somewhere, it will still tumble at some basic tumbling rate. So that's the psi 0, and you can also estimate this quite well from experiments. And then now this phi is the perturbation of that. And this epsilon is small. And so then we're doing a rescaling of the time and the space, and we obtain this kinetic equation now where the solution depends on epsilon. And we would like to take the epsilon to 0. And yeah.
And the model, the n dependence of q, I missed it in the run and tumble equation. How
okay. I have not made my slides in a consistent way. So, you know, I just showed you S everywhere because I wanted to do the argument just with the influence of the S, but you can also do this with the S and the N. So I should have, to be consistent, I should have taken out this N here out of the Q.
For the moment, there's not.
And then later tell you that you can do the same thing for S and N. I mean, you know, the influence is in the same way. Okay, so let's put the food back in. And what we get then is, in the limit, this macroscopic equation. So this is not something that I proved. This is a team in a paper from 2010, so already a while ago. They showed this macroscopic limits. But what is very interesting is now what you get, because this looks very similar to the classical Butler-Keller-Segal model, with the difference that now the drift term, this function u of S and u of n, is potentially a nonlinear function. So it depends on this phi, and the phi comes from this microscopic assumption on how the cells tumble, essentially. And so first observation is that if this phi would be linear, then you recover the classical model. And so what you see then is that essentially the classical Butler-Keller-Segal model is a linearization of this description. And the good news is that this model actually allows for traveling waves. So, and you can go even more specific. You can now estimate what this phi should be as a function from experimental data, and then solve this model, make, you know, numerically, and compare that with the actual observations that you have from the lab. And they did that for the choice of phi just being the sign function. So this is called a stiff response, because what it basically says is that if your cells detect that the chemoattractant is suddenly increasing instead of decreasing, or the other way around, so the derivative of S changes sign, you immediately react, right? So you don't care like of the magnitude, the gradient, you just care about the sign. And of course, that's, you know, maybe not what actually happens, but it seems to be a good approximation, because if you now compare, so this image here is the black lines are the numerical solutions to this model, and then the dots are numerical experiments. And so this is the tube again. So the blue, the green, and the red are the densities of cells that were measured at different time shots in the channel. And you see that it's a very good agreement with a few cells that stay behind at later times because we didn't consider any cell death in the model. Whereas in reality, that might actually happen, or yeah, it's real life in the end, so other things might happen. Okay, so what we're interested in now with this type of model, with the stiff response function, is the cluster formation. So again, if there's no food source, then either you have diffusion or you have attraction. And there is some nice also experiments that look at these stationary patterns. Yeah, but I don't want to go too much into this. I want to tell you now about what we actually did about this model. So this is recent work with Vincent Calvez that started actually thanks to collaborations with José. And this is to appear in the Annales mathématiques de la Faculté des sciences de Toulouse very soon. I mean, it already got accepted recently. Okay, so now this is the model that we actually look at. So now you know where it comes from and why it's interesting to study this. So we make the same assumptions as before. So no nutrient and the chemotaxis is in quasi-equilibrium. We put all the constants to 1. I mean the diffusion constants, because we're not biologists, we're mathematicians, we can do that. And then if you actually care about the constants, you just put them back in later. It doesn't make any difference for the analysis. And because this is already hard enough, we just do everything in 1 dimension. So the reason why this is an interesting equation to study in terms of, the mathematical challenges for the analysis would be because you have the sine function in the drift, and so that makes it a discontinuous drift term. And so, yeah, that is sort of what we have to get around. And then also here, so this alpha is the chemical degradation rate, if I remember correctly. Yes. So the chemical S will react and sort of degrade as part of the process. And so you have to take it out of the equation because it will react to something that the cells themselves cannot sense anymore. You can also put that to 0 if you can assume that you're on time scales that are small enough so that this doesn't play a role. And so this is what I did previously when I said we're just solving the Poisson equation. So now if I have a positive alpha, then we're solving a slightly more complicated equation. It's still okay because there's a fundamental solution, and you can write that down. And then substitute it into the first equation, you're essentially looking at 1 equation. And what we want to do is show convergence to equilibrium. Right, and because of this discontinuous nonlinearity, we have to find some good approach. Okay, so the first question, of course, is, okay, what are we converging to, right? Luckily, in this setting, we know what the stationary states are. It's a whole family. 1, you can shift things, of course. So this A is just a shift parameter, but we can just put that to 0, essentially, if we want. And then the other parameter is the mass, right? And to be convenient, we fix the mass to be 2 over chi. This way, we don't have the constant in front of the exponential. Okay, so really what I'm focusing on today is simply this convergence questions, and in particular locusability. So no questions about existence, uniqueness, or regularity. And something to observe is that if your initial data are nice, then the solutions will remain continuous, but the derivative of the solution is expected to develop jump discontinuities because of this sign term in the equation. So it's not C1, that's what I want to say. And what we're trying to prove is a result of this type. So if in some convenient norm, you start already close enough to the equilibrium, then you will have exponential convergence to equilibrium with some rates that you can specify in terms of the parameters of the model. So that's the goal. And here's the key idea that actually makes this work. So the key idea is to essentially split the problem into looking at the evolution of the shape of the solution and the evolution of the center. So what we will work with is this x of t, which I will define to be the maximum of the chemoattractants. And okay, the first thing is there only one or is there several, right? Because that would make things more complicated. And for this approach to work, you really need to have just one peak. And then you analyze how this one peak moves. And what you can show, and that was not so obvious at the beginning, is that if you start with a chemoattractant distribution that has a unique peak, then this will also be preserved over time. So it's simply an assumption for now that we make on the initial data, essentially. And so once you know that your S simply has a unique maximum, then you know that, okay, before on one side you have the sign that is negative, on the other side you have the sign that is positive, and you're essentially looking at two different equations that are coupled to the position of this x of t. Right, so I would tell you more about the x of t in a bit. I will not talk about the case alpha equal to 0. There are some sort of ways of handling this by reformulating the equation as a scalar conservation law. For alpha positive, as I mentioned, you can actually solve for the chemoattractant using a fundamental solution. And now what we need is sort of some expression of what this x of t actually is. And well, it's simply the point such that dxs is 0 at that point. And so then we write down what that is because we have the explicit expression differentiated in time. And this is how we get an equation for the x dot. And since I said that the derivative of rho is not necessarily continuous, I have to make clear here, like if I go from the left or from the right to the x of t. So we have an evolution for the chemoattractant peak. And we will study that separately from the evolution of the shape. So to understand the shape, we go into the moving frame. So now I shift everything, so the center is always at x of t. So y is now the variable that we look at, and then this is the equation that it simplifies to. So the whole trick of analyzing this is by doing a lot of reformulations, essentially, yeah?
I have a question. If alpha is 0, do you still need the assumption on the initial data?
With the unique peak?
Yes.
Yeah.
Yeah.
Yeah. I mean, if you want to do this argument of splitting the shape in the moment, then yes. If you allow yourself to regularize the sign, that's when you can use this scalar conservation law approach, and then you get L1 stability instead.
Okay.
But here, essentially, in all the arguments, you can take the alpha to 0, and it will still.
But you still need the assumption. It doesn't shape up nicely immediately as soon as you start the process. This was my question.
Oh, you mean if this proposition holds for alpha equal to 0? This one? Does it still propagate?
My question is that if alpha is 0, assume you start with around initial data which don't have this nice shape, right?
So you have several peaks, let's say.
For example,
yeah.
I wonder when t is strictly greater than 0, you don't get something nice immediately.
So that's an open problem. That will be listed on my last slide as something that we would like to understand. Okay. So from numerics that I can show you if there's time, we can see that usually if you start with several peaks, they will merge to one essentially. So the conjecture would be that there exists a positive time like large enough such that you will only end up with one peak. But so far, all I can tell you is that's what the numerics do. But that's not a proof, right? So yeah, if you have ideas on this, actually, I think that would be the missing piece in some sense to complete the story on this. Yeah, it's a very good point. Okay, so this is just an overview of the shape equation, the equation for the movement of the center, and then the steady state now in the moving frame. And so, cutting to the chase, this is the theorem. And then the rest of my talk will be to convince you like how we prove this. So the norm that we work in is some weighted H1 norm, where we weight by the steady states. And so we assume that the initial data then is close enough to equilibrium in this weighted norm. And then we're able to show exponential convergence to equilibrium. So That was sort of what we hoped to do. And we were able to do that using energy estimates. And you can see here that we have an upper bound for this gamma, which depends on the chi and the alpha in a very explicit way. And we also know that the x of t converges to some limits, but unfortunately we have no explicit expression of what this x infinity is. Maybe there is an expression in terms of the parameters. And so some remarks on this. Yes, already you said some of this. So if you look at the expression for this optimal, like upper bound for the gamma, you can ask what happens if you take alpha to infinity or alpha to 0. And you see that if you take alpha to infinity, then it's chi squared over 8. And if alpha goes to 0, then it's chi squared over 4. Yeah, exactly. That's what there. You can also look at the limit alpha going to infinity in the equation itself. And then you obtain this equation for rho, which I don't even know how to analyze this. I mean, we haven't looked at this equation at all, but I think this would be another sort of interesting next step. Because I would imagine that the regularity of this is not very nice. Anyway, that's a different story. That's what you would get in the limit. Okay. So yeah.
The x of t was the by the peak s, or?
So it's the peak of the chemotractant, the S, and then the rho is the distribution of the cells, and the cells will behave depending on where the peak of the chemotractant is, because they always want to go where the chemotractant is the highest. So you would expect that if you have a peak in the chemotractant somewhere, that then the cells also concentrate around there, and most of the mass goes there. Yes.
But the chemotractant is also moving.
Yes, they both. I mean, the chemotractant is being produced by the cells. So then if more of the cells move to the center or the peak, right, then more chemotractant will be produced there. And so there's a feedback, of course, between the cells producing the chemical and then the chemical influencing where the cells go.
But an x of t having a limit, but t going to infinity means that the whole thing at some point comes to a halt.
Yes. I mean, you have to have that, right? Otherwise, you don't have stationary states. I mean, maybe it's not obvious that should happen, but it does happen. Yes. Yeah, that's exactly what it means. Yeah.
Yeah, so do you have an estimate of the peak of rho versus the peak of S? Or some relations that you know?
I mean, we didn't write this down explicitly, because the peak of the S is what determines everything else in a way, but I think you can translate that statement. I mean, I think it's easier to look at the peak of the S because the way how it appears in the equation, right? Because you look at the sign of dxs. Might be possible to write down the peak of the rho in terms of the peak of the S, but I think it would be sort of an extra step that doesn't help directly in the analysis, because we need to know where the S changes sign for the equation. Yeah.
When you look at the linearized equation, this peak condition also appears as a stability condition for the linearized equation?
Yes, it does. Yeah. We looked at the
modes where there's not one peak, but something else. You have exponentially growing.
Oh, no, we didn't look at it for several peaks. Do you mean that?
I mean, if you linearize the equation, then this one peak condition is a stability criterion, or?
Yeah, that might be. So what we did do is we looked at the sort of spectral analysis for the linearized equation, and then you get a spectral gap, which is chi squared over 4, which is sort of the limit what you get in the alpha also here. But the x dot still plays a role there. It doesn't disappear as you have a linear part that has the x dot in it. Yeah. And then the x dot also goes into the nonlinear part. Yeah. There's also a paper by Christian Schmeiser and Gael Raoul and Vincent Calvez, who looked at this model, and the kinetic version of it, but decoupling the rho and the S. And that makes it then easier and removes that issue as well. Yeah, and something that I should say is that I think our gamma is not optimal. And one reason for that is because the way how we get it is by using two separate inequalities. And in principle, you could try to derive just one inequality and try to find the optimal constant there. And that should probably give you an optimal gamma. But we decided not to do that because those two separate inequalities have meanings by themselves. And I will get to what that is. Just, yeah, as a comment. So very important here is the conservation laws. I mean, one is conservation of mass, one is invariance by translation, and we need to use them in different places for the energy estimates and the function inequalities. But what is interesting, I think, in terms of the analysis, is that if you, once you do this shift to the moving frame, you get different weights. Like these are in different functional spaces, right? One is weight 1 and the other one is e to the minus square root of alpha y. And so at the beginning, if you look at this and you want to make use now of these conservation laws, it's not clear like in which of these weighted spaces you should pose your energy estimates. So one is more natural than the other one, I would argue, because you should kind of use the space that weights everything with your steady state. Is this already the renormalization? What are we looking at? No, we're doing this in a minute. So yeah, so one other sort of nice result as part of this that we use is a weighted Poincaré inequality. And I mean, there's so many versions of Poincaré inequalities. Probably somebody has proved this somewhere at some point. We couldn't find it in the literature, so we just proved it again, I guess. So if any of you have, knows the reference for this, then I would also be interested in that. But the idea is that we use a Poincaré inequality where the weight is different from the weight of the appearing in the inequality is different from the weight in the mean. You subtract the mean. And what that allows you to do is to transfer the information of one of these conservation laws into the space where you need it. So that's kind of a key trick here. Okay, so maybe I'm not going to talk about all the details of all of these. I want to give you, I can sort of skip over the fourth part. These are the key steps in the proof. So how do we get this convergence result? The first step is just a reformulation of the equation. That's pretty straightforward. But I want to show you the Poincaré inequality that we actually use and then how we use that to get the energy estimates. When do you want me to stop? I don't know what the... Okay, perfect. Okay, so the first thing we do, because we want to work in this weighted norm, we divide by the steady state, and we know what it is, so that's very nice. And then we can rewrite the equation. And what is nice is that, as I said before, the rho is not necessarily, doesn't have continuous derivative at the chemotractant peak. And this actually corresponds also to what you saw in this tube experiment, that the profile is asymmetric, so something like that. So the derivative is discontinuous. But now if you divide by the steady state, now the derivative of the u is continuous. So you're exactly taking out the correct, the discontinuity. And then the steady state is just 1, of course, for this. Okay, and now I'm just rewriting the same thing. So I call lambda the chi plus square root of alpha just for convenience. And I introduce some notation for a mean with respect to this some exponential weights. And now the two conservation laws that I showed you before become simply two statements about means in two different weights. So one with weight chi and the other one with weight lambda on the derivative. And so here comes the inequality. So if this lambda here would be a chi, then this would be just classical Poincare inequality with exponential weights, right? But this is actually, okay, before I go into why this is called improved inequality, I mean, the fact that the chi-squared over 4 over chi-squared is an optimal constant, if alpha is equal to 0, which says that lambda is equal to chi, you can see this by just doing direct spectral analysis on the operator. So you can prove that directly. Now, why is it an improved Poincare inequality? It's because of this statement. So anything that I put there which is not chi, for the mean, I mean, is the stronger statement for the inequality. Because of the fact that anything that I can subtract here to take the infernal, and I get exactly the mean with respect to the chi. So if I take, so this is the limit sort of alpha going to 0, so lambda equal to chi. This gives me the classical Poincare inequality with the exponential weight. If I go the other direction, so alpha going to infinity, so lambda going to infinity, then you can recover a Hardy type inequality out of this. Yeah, as I said, if you know any reference for this inequality, let me know. Actually, if you don't want the optimal constant, this is very easy to prove. If you want the optimal constant for this improved Poincare, then you have to do a bit more work. Okay, so now how do you use this to actually conclude for the decay estimates? We do another reformulation. So now we look at the perturbations around the equilibrium, since we want to start small. So now this V is the perturbation around the equilibrium. The W is the derivative. And again, I write down now the evolution for the shape, the evolution of the center, and the conservation loss. And now we have to do energy estimates. And to find out exactly which energy to use and what's the right way to estimate them, that was sort of the challenge at the beginning. And now after we know how to put all the pieces together, it seems to be, everything works out very nicely. So we have 3 different energies that we looked at, the L2, the H1, and the H2, essentially, in these weighted norms. And what you need to use is the H1 energy. And the reason for that is because you need H1 in order to control the nonlinearities that come essentially from the movement of the center, so this x dot. So if you want to estimate the x dot, you get a term that is H2, that is positive, and in order to control that, you need a minus H2 norm term, which comes when you differentiate the H1 norm. So that's the reason why we use that. And so if I differentiate now this energy F, then I get the minus 2G, which gives me my decay. Then the W evaluated at the chemotractant peak, which is now 0 because we're in the moving frame. That's the non-local term. And then the J is all the nonlinear terms, which I will not write because it's a mess. It's a very long term. And then we use the improved Poincare inequality together with the second conservation law to get one estimate. So basically looks like a Poincare again, and then the classical Poincare with the first conservation law to get E controlled by the F. And here you see how the improved Poincare inequality allows you to use our second conservation law, which is in a different space than the first conservation law. So that's why we need these 2 inequalities. And then you have to do a lot of work to control your nonlinear terms, which also I'm hiding, but I can tell you that you can control it this way. And in particular, you get the G here, right? So this is why you need to use the H1. And then you put all of this together, and that's how you get the estimate. So that's sort of several pages of proof in one slide. Now maybe just some numerics. So here we started with the density. So the black line is the density at time 0 that has 2 peaks to get your question, to answer your question. And then the red one is the density after some time, and you see that it immediately goes to something that has just one peak. And this is the same thing, but now just for the sign of the chemotractant, the derivative of the chemotractant. And it's the same thing at the beginning. The black dotted lines tell you where the S changes sign at the beginning, and then you see that you just have one place where it changes peak. And here you have the location of the peaks, and so you see that one of them disappears. Sorry, this is the location of the same change of sign here. Okay. And then we just checked how well we're doing with the rate of convergence. And the yellow line is what the proof tells us. And then the blue and the red is one L2 distance and the other one the Wasserstein distance. And so, it's a bit better than what the theorem tells us. Just to get some rough idea. And yeah, so the first one is exactly your question. Can we show that more than one chemotractant peak exists? I would guess no. I mean, can we show that it doesn't? That's, I guess, a better formulation. Yeah, can we get an optimal rates? And the third one is what I'm currently working on with Vincent Calvez again and Gianluca Fabre. So we're looking at the underlying kinetic model. So if you substitute the sign function, the stiff response function, into your kinetic model, you can also do the analysis immediately there. And now if you want to do convergence, hypocoercivity is kind of a very natural technique to use there. But then the problem is that it's actually a nonlinear equation, and hypocoercivity is, as a technique, is made for linear equations. And so there's already one challenge there. You need to control the nonlinear terms. And for general velocity sets, you don't even know what the steady state is explicitly. If you can't write that down, then how do you use these approaches? So we started with the two velocity model that you were also showing earlier. And for the two velocity model, we have an explicit steady state. And so I think we're able to now get to a convergence rate there. Just sort of the last 2 weeks, I would say we made some good progress on that. So hopefully we'll be able to say something. But for the general model for any velocity or even simple velocity sets, but more than two velocities, yeah, we don't know how to do that at the moment. Yeah, and I think I finish here with a pretty picture of some cells. All right. Thank you very much. Are there any questions?
No, I'm just trying to. These are cells?
Yes.
So these are cells that have been injected with different types of fluorescent proteins. So like the classical one is the green fluorescent protein.
Yeah.
You inject them and then you shine some ultraviolet lights on them and they glow. But you can also, you can paint with cells essentially, injecting like different types of proteins into them. Some people in San Diego had fun.
How do you know where it's discovered, like the food in these particles?
I guess you have to take the picture very quickly before they get too hungry, right? Like, yes.
Since it's been a while, I haven't seen the problem, so I was thinking in a different way. And since there are two experts in that type of equations here, do you think that there is some connection with the free boundary problem you separate into two pieces of the XT? And you look at the boundary condition there. So Marie-Thérèse and Maria Guardani did something related problems years ago. I don't know. You just separate into two and then look at the boundary conditions. Maybe one can reflect it as a free boundary problem.
Yeah,
You could, I think. It's a couple.
No, I decided for a plant.
Yes.
The glowing condition.
Yeah.
Yeah, so you have basically two different equations with the boundary condition at the x of t. And then the equation for the x of t itself depends on the solutions of both of these. That's basically what.
And so has the feeling of some of the problems that we were looking at years ago. Okay.
I mean, we definitely need some new tools or perspectives in order to do the kinetic equation in general. So
that is different, yeah.
No, that's different. That's good.
But 2D, I mean, you did the analysis in 1D.
everything in 1D.
I think linearly symmetric solution probably you can do similar machinery as it did or not. It seems that the stationary states would do something to get radial stationary states. With many chemotaxis models, you just argue that this is radially symmetric anyway. So have you thought about that?
The short answer is no, we haven't thought about it. But you know, the 1D case makes things a lot easier because then you just split it with this x of t, right? Now, if you're in 2D already, you have to think a bit how you
But
deal
what
with
is the sign function in 2D? Sorry.
Yes, that sounds good.
What is the model into? Now you have the sign of the derivative, right? So when you have in higher dimensions, what is that?
I think it's just a component-wise.
Sorry.
It's a component-wise sign.
Ah,
so you take the sign of the gradient. Yeah.
Okay, in component-wise.
Yeah.
I see.
I think so. I'll have to check, but I think that's what you do. Yeah. Oh, so good question, yeah?
Non-expert question. Initially you showed some pictures from some experiments showing that they're traveling waves. Could you ask the travel, or can you ask the traveling wave question in your PE? And do you get maybe I wasn't listening properly.
No problem.
Can you ask kind of stability questions or and answer them?
So the first answer is yes, there are. You can show the existence of traveling waves.
Yeah.
Does this answer it? No, because we took the food out. So traveling waves don't exist without food, right? So you need to have the nutrient on one end, and then you. So then the questions of convergence to equilibrium is different one. You would have to.
The stability of the traveling wave.
Yeah. So
you have to move to the traveling wave.
But I think that should be possible to do in a similar way, I guess, right? Because you can think of it as.
But just out of curiosity, you showed the kinetic model as well that is derived in the closed paper or something. So there you have the nutrient. If you would take that out, is the nutrient the significant? It has to be significant to get the traveling waves.
Yes, yes. Without nutrient, no traveling waves.
Formulation.
Yes, without nutrient, no traveling waves.
Yeah. Sorry, just.
Yes.
This equation has kind of sigma being constant are solutions, yeah? Not sigma, a rho. Levels of rho are constant, so we could ask kind of whatever the Riemann problem question, yeah? So you have something there. And then
it's not constant. I mean, the raw, you would expect that it looks like that, right? Like two exponentials meet like an exponential.
If I'm ignoring your steady state that you're interested in it, and I'm looking for other constant solutions. So rho being constant is a solution as far as I can see. Yeah?
But this is on the whole space. So then the mass would be infinite, right?
Yeah, well.
Unless you're on a bounded domain, and then it's a whole different issue because then you have boundary conditions, and then
Yeah, but whatever this for classical reaction diffusion equation, you do the same thing. Yeah, so that of course you're posing a long tube, you think it's infinite, and that's nicer, and then you forget about the concept of mass. Yeah, so this is.
So you're thinking of steady states on an infinite domain with infinite mass.
And then kind of then I would hope that maybe kind of having infinite mass one could also have traveling waves for without nutrients. I forgot about nutrients. I just worked on this way.
I have no idea. I mean, you need the finite mass in order to think of it as a probability measure, right? Also. Yeah, we have a traveling wave towards the food source now.
We have only 1 minute left to stay here, so.
There is another.
Okay, thank you.
Thank you.